Thank you to the organizers for having me here. Um, it's again a Euclid talk, but I'll stick to the theory side, assuming we have wonderful data and systematics and everything under control. So I'll tell you all the problems that we have on the theory side. And speaking of theory, um, we are here now talking about all these wonderful measurements and about our universe and what we can observe and what we have learned about it, thanks to really the theory of general relativity that was introduced by Einstein a century ago. This provided us with a theoretical framework that allows us to really address the phenomena that had fascinated people for centuries, the phenomena in the sky. And we like to think of the introduction of general relativity also as the time when physical cosmology was born. And the first experimental observation and confirmation, actually, of physical cosmology really came when Hubble measured the recession velocity of distant galaxies. Then, fast forwarding from 100 years ago to today, we have collected an impressive number of wonderful measurements, from the cosmic microwave background to the clustering, to the lensing, weak lensing, rotational curves of galaxies, and so on, that allows us to really understand the universe, more or less understand how it formed, how it came to what we observe around us today, and to compress all that information in a very simple, wonderful standard model of cosmology that is the one that we call lambda CDM. So these are impressive successes that left us also, though, with a pretty dark universe. And we have seen already this cosmic pie. So if we take lambda CDM to face value, really means that we are not really sure about what is making up 95% roughly of the current energy budget in the universe. And of this 95%, I like to focus on the 68% represented by what we call dark energy. That is typically what we associate with the accelerated expansion of the universe. So the idea here is let us use all this wonderful data that will be delivered to us in the next years, not only to test consistency of the data with the standard model of cosmology and perhaps further refine the parameters that characterize it, but also perhaps to keep an open mind and remember that general relativity, the theory that we are using to obtain, to describe the universe and make all these measurements, has really been tested with great accuracy on the solar system scales and around astrophysical complex objects. We then need makes a sort of leap of faith of several orders of magnitudes in the characteristic lengths and curvatures, etc., that characterize local tests, and assume that GR is valid also for the scales that are important from the universe. So let us keep an open mind, and besides checking for the consistency of lambda CDM, let us also try to explore the parameter space that is allowed to alternatives and try to see whether we can shed some light on the nature of dark energy if we need it, if it's something different than cosmological constant, the source is cosmic acceleration, but also to make sure that GR, general relativity, the way we know it, the way it was formulated by Einstein, is indeed the correct theory, and whether we need to modify to some extent in order to explain what we see. And that's really important to get it right, because many of the things that we infer also about fundamental physics, masses of neutrinos, etc., from the universe, rely on our assumption of general relativity. So we have a pretty dark universe in front of us, but we are also living this golden age for observational cosmology, where really an impressive lineup of surveys will provide us with exquisite measurements of the expansion rate, which is basically the thing from which we learn about the accelerated expansion of the universe, but furthermore also about the lensing potentials and the growth rate, as we have already heard. And there are many surveys that will be launched or that are already ongoing and finishing now. And what is really important, and I'll try to stress towards the end of the talk, is also, I think, the synergy among these experiments. They go and probe different regions, different regimes, especially different regimes for the theory of gravity. So I think it's very important to keep in mind that we might want to combine information coming from all these surveys. So, as I was saying, testing lambda CDM, but also try to go beyond and see what is the parameter space allowed to alternatives. And we can argue for why, but also one of the reasons is because we can. We will really have a lot of information gain in the upcoming years. And this is a way of showing, in terms of bits, how much information, cumulative information, we will gain through the years on some alternative extensions of the lambda CDM, of the standard model of cosmology, going from massive neutrinos to, this is the typical dynamical dark energy parameterized in terms of the W0 and W8 that we have already seen, and so on. These are some. Ojava is a model of modified gravity, etc. So really we are here now. Here is when basically we made a big jump in establishing the standard model of cosmology. Now we are approaching a next jump and opening a lot of information on alternative. And perhaps we can start discerning among them. And also, as I was saying, we are really talking about testing gravity in a new regime. In a new regime that is down here, and in terms of potential and curvature that we are going to probe, is orders and orders of magnitude different from other types of regimes where we have tested gravity. So, speaking of this new regime that will be probed by missions such as Euclid, what are the important quantities that we are going to observe and measure? And I like to focus on linear scalar perturbations, although, I mean, then of course the nonlinear is a very important aspect, but let me start from the linear one. Linear scalar perturbations around the homogeneous and isotropic universe that is expanding. So if I start from the flat homogeneous and isotropic universe, I can characterize it by the scale factor A, which is a function of time, and it tells us basically if we measure how it changes with time, it tells us about the expansion history and how the universe grows and at which rate it expanded. Then we can go beyond this homogeneous and isotropic universe and start perturbing it. And as long as we are interested in structural growth, in understanding how the galaxies and clusters that we observe around us have formed, and how they bend light that is reaching us from distant sources, then we can focus on these two scalar perturbations to the metric, potentials phi and psi, which are functions, since now we are perturbing, are functions not only of time but also of space. And we have heard a lot about clustering and weak lensing. So when we look at the growth of structure, the formation of the galaxies and clusters of galaxies, and at the peculiar velocity that these galaxies have, which are things that we can measure if we look at the clustering, then we are really looking at non-relativistic probes of our theory. We are really probing this potential psi, which enters here in the time-time component of Eurometry. When we talk about weak lensing, and similarly about the integrated Saxoff effect in the cosmic microwave background, we are really instead looking at the dynamics of relativistic objects, such as photons. So those respond to this combination phi plus psi. The geodesics of photons, for instance, are affected by this combination, conformal combination phi plus psi in the metric. These are the things that Euclid will allow us to measure very well through weak lensing here and galaxy clustering here. And in a quite general manner, we are very familiar with talking about the expansion history and encoding the fact that it is sourced by the cosmological constant in saying that the equation of state of dark energy is constant and equal to -1. So the equation of state is really telling us about the rate of expansion. The h is related to how the scale factor changes with time. And this is the effective equation of state. At late times, when we observe the acceleration, when matter doesn't dominate anymore, it is dominated either by a cosmological constant or some dark energy component. And if it is the cosmological constant, W is constant and equal to -1. So that's something that many missions are after, and you have seen many measurements of W and constraints on some parameterization of it, such as the W0 and WA. If we go beyond the expansion history, we can similarly, in a quite general manner, encode informations about any deviation from the standard model of cosmology in two functions now, as long as we care about large-scale structures, so clustering, weak lensing, etc. Two functions that now need to be functions not only of time, but also of scale, because we are talking about perturbations. And the simplest way to introduce them is by looking at modifications to the Poisson equation, which is the one that relates the Laplacian of the potential to the density contrast perturbations in the matter, and similarly an analogous equation for the lensing potential. So how much a given density perturbation sources in terms of lensing and deflection of light. This is the thing that determines the path of photons. So all these functions, W, mu, and sigma, would be equal, would be constant and equal to 1, actually W equal to -1, if the model is lambda CDM. As soon as we deviate from there by introducing some dynamical dark energy to source acceleration, or we modify the theories of gravity, these functions are something different from the lambda CDM value, and they typically are function of time and scale. So not only W will depend on time, but also we have learned the growth of structure will be more interesting, more complicated, and it's not really simple to see it here from this equation that I've written down here, but really the one key thing that we have learned from modifying, from going beyond lambda CDM and looking at how things cluster, is that the growth rate, something that has been mentioned before already, becomes scale dependent. Different modes grow with a different rate, which is not what we see in lambda CDM. And also there's more richness out there in the dynamics, not only of the background, but also of the structure formation. It's in lambda CDM, once I have solved for the background expansion history, I know exactly what rate of growth to expect for my structure. There's a sort of consistency relation which is broken as soon as I abandon lambda CDM. And also very importantly, since this function mu and sigma can be different from one and different from each other, relativistic and non-relativistic probes may respond to different functions in your metric. So that's behind the importance of combining clustering and lensing to try to compare those functions. So, okay, I think we have shown this picture many times this morning. So you know, by now you know very well the spacecraft, etc. for Euclid. So, well, and also we have already discussed that it will be combined mostly weak lensing measurements and galaxy clustering. It's coming soon. I keep it broad and open. And it will really be wonderful in terms of measuring the clustering and weak lensing. Now, as Hank said, dark energy introduces subtle differences. So it's really a tough job, that one of capturing those subtle differences. And here I'm going to show a difference between the outcome of an M-body simulation done in lambda CDM, and this is a snapshot at redshift 0, so today, with respect to what you would obtain if your universe was instead described by a modified theory of gravity that is f of r. And you see the differences are quite subtle, and this is a very, it's a sort of an exaggerated model of modified gravity. We are not really, we know already from other measurements that we are not really allowed to modify, to boost an FOR, pump an FOR to such a level. But and I would say they are already subtle. I think I have also the full dome images for this. I'm not sure how this will work. Yeah. Yeah. So we can train our eyes to see the differences and capture them. Yeah. Thank you. So it's mostly positions of the filaments and some some density of the halos. So, okay, but Euclid, so these are subtle, but Euclid can do it, and also with perhaps using the synergy with other missions. And here is the result of some forecast done recently using not the most up-to-date specifications for Euclid, but some intermediate specifications for Euclid. So we are now going through an extended forecast effort, and we will have further results. But this is showing how well mu and sigma, these two functions that were parameterizing how clustering departs from lambda CDM and how clustering departs and how lensing departs from the lambda CDM scenario, how well Euclid will measure them. So these I think I had a legend, but it's not really working well. These vertical lines here are what clustering gives you. They're mostly basically as we build these functions, the mu is mostly linked to clustering, and sigma is mostly linked to weak lensing. So here, these contours here are weak lensing. And then this is combining galaxy clustering weak lensing from Euclid with Planck. So we go really in and zoom in, and there's some orders of magnitude improvement in the figure of merit. So we will reach percent accuracy on W of A, and in the order 1 to 10% on mu and sigma. So also, as I was saying before, there's other missions out there, and there are interesting synergies, and the one that I want to mention is that one perhaps with extremely large telescope that will allow us eventually to measure redshift drift and to sort of access what is called the redshift desert for dark energy. So collect information about W, the expansion and the rate of expansion at higher redshift, something like 2 and a little higher. And that is just by looking at how the redshift of a source changes just because of the expansion of the underlying expansion of the universe. It requires years and years of measurements. But anyhow, so the point is we will have, okay, I've been very slow. We will have wonderful numbers. And are we ready to extract the correct physics out of these numbers? That's the question that I'll try to address. And let me give an example from some results that came out of Planck a couple of years ago, and I think now they will, in a few weeks, release updated ones, which was by measuring these two functions, mu and sigma, here. And this is an alternative one. It's a combination of mu and sigma, this eta, the gravitational slip. They seem to find something, so lambda CDM would be here. They seem to find the data prefers something in that quadrant. So if that's the case, if that remains, and if we shrink those error contours, are we ready to interpret what that means? Are we ready to extract physics from there? And I think we have made a lot of progress and for that, and we have understood that the main starting point is to declare our ignorance about the dark universe that we are facing. But declare it in a sort of structured and informed way. So it's a sort of step back from what happened in the last 20 years from the discovery of cosmic acceleration, where dozens and dozens of models were proposed that try to explain this acceleration with something different from the cosmological constant. Now I think we paused and we understood that we are sort of in the dark, but we should use first principles, and in particular use symmetry principle to try to guide us and organize our ignorance about what this dark universe is. Because then perhaps we can use this to fit something more powerful to data, more than just going there and fitting random pet models to data. So this is one way of declaring our ignorance in a very organized way. And I won't enter into the details, but let me just say that we are putting all our ignorance about what dark energy could be in these red functions of time. And these are just operators. This will be the standard model, the Ricci scalar, and the constant, the cosmological constant lambda. And then you start opening things. You start giving dynamics to your dark energy. You start coupling it in a non-minimal way to gravity. You start giving it some really non-canonical kinetic terms and so on. That's what all these operators mean, but I really don't want to enter into those details. But this turns out to be a very good way of organizing our ignorance about dark energy, and it allows us also to keep always physics there. So we are facing still unknown functions, but we can control them, and we can control the stability of the physical viability, if you like, of any model that we are trying to fit to data. Because we have an action now describing this dark universe, and we can control some things such as whether this action and this theory will develop instability, something that grows exponentially, or whether it will be a physically viable theory. And this is one way of doing it. I'll go very quickly, but it allows you to really cut down on the parameter, on the theory parameter space that you want to fit to data, and don't waste time into fitting things that don't make any sense from the theoretical point of view. But also, I'll try in the last few minutes to show how we are using this framework, this action that parameterizes what dark energy could be, in order to trying to learn what to expect for those functions mu and sigma, which features should we be after, and whether do we really expect mu and sigma to go in the fourth quadrant of that panel that I showed before from Planck, etc. So the way in which we are using that framework is by generating large ensembles of statistically independent Hordensky models. Hordensky is a very popular model of modified gravity. Basically, it encompasses all scalar tensor theories with second-order equation of motion. So whenever you go beyond lambda and introduce a dynamical scalar degree of freedom, whether it comes from modified gravity or really thinking about a dark energy field. Anyhow, so what we are trying to do in terms of that action, they will be characterized by some 5 red functions of time, and then we try to parameterize those functions, expanding them through in different ways around today, around early times, etc. So I don't have time to go into the details, but in some way we create a large ensemble of something like 10 to the 8 independent Hordensky models, and then we look. Sorry, it's not showing. The white parts are not showing very well, but we look at what these models and subclasses, so this is the full Hordensky, but we divide also in some subclasses, simpler Hordensky with canonical kinetic terms, so this is the popular generalized Bronsdicki models. We look at what they predict for, and now, oops, sorry, I really mislabeled this. So the model should go in the vertical. This is generalized Bronsdicki, this is a subclass of Hordensky that obeys gravitational waves, and this is full Hordensky. So here you have mu, the function describing deviation from clustering. It is equal to 1 in lambda CDM. Here you have sigma, and here you have the equation of state. So we are jointly creating these distribution functions for what to expect for W and what to expect for mu and sigma. And we are trying to extract information out of this. So here it's redshift 2. So you see that something interesting and some interesting deviation from the -1 constant that characterizes the cosmological constant happens at higher redshift. And here we are also learning something about the shapes for mu and sigma. And really what we are trying to get out of all this is mostly correlation lengths. We want to understand how, in different models, how much these functions are correlated. So if looking forward to binning them and trying to reconstruct them in a non-parametric way, I can try to use this as a theoretical prior to combine with then the data covariance matrix and try to guide my reconstruction through binning. And okay, so do I have still a few minutes? Okay. So let me just touch upon, since I mentioned synergy, I think something very interesting that happened in the last year. As you all know, almost a year ago now, there was this detection, joint detection by LIGO and the Fermi gamma ray burst monitor, and then several telescopes that observed the electromagnetic counterpart of the merger of binary neutron stars that had emitted a gravitational wave that was picked up by LIGO and Virgo. So really now, if you like, after straining our eyes, it is also almost also time to strain our ears. So, and the interesting thing is that since they could localize very well by this joint multi-messenger sort of observation of this event, they could measure the redshift of the galaxies that hosted this merger, and they could so hence localize it very well. And that allows to perform a lot of physics, and in particular the one I want to mention is that this allows to put constraints on the speed with which gravitational waves propagated from the merger to us. And looking at how gravitational waves described by this traceless transfer tensor propagate on a cosmological background, we can use the time delay, the very small time delay between the gamma ray burst and the gravitational waves to place constraint on how much the speed of gravity could differ from the speed of light. And it's almost zero. I mean, it's a very tiny number. Now, why am I mentioning this? Well, because interestingly, this measurement has some quite consequences for many of the models of modified gravity that we have been thinking about. And as we had been thinking about them, Hordensky mentioned it, when trying to address the phenomenon of cosmic acceleration, or anyhow thinking about how gravity could be modified on the large scales. And yet the measurements in a completely different regime is coming to us and telling us that we might have to cut down some of the theory space. Because the models that we are treating and that action that I showed you before doesn't affect only scalar perturbation to the metric, but affect also the tensor. And the way it affects it is by changing this friction term here, but more importantly, these are the functions in red that I showed before, by changing the speed of gravity. So this is how the gravitational wave measurements impacted on Hordensky, cutting down some of the interesting models out there. There's a lot left, but I think it's what we have learned is that synergy is very important, and what this measurement is helping us in doing in terms of our large-scale structure functions is narrowing it down a little bit. And this is showing, for instance, again, that huge ensemble of Hordensky models for which we studied the behavior of mu and sigma and jointly of the equation of state, how it looks if now I go like Planck, I look at the quadrants with mu and sigma on the axis, mu and sigma equal 1 here, and I'm doing it at different times. So here is today, here is earlier times, and different scales, large scales, small scales. Don't bother about the difference between blue and white, focus on the white. And this is telling us that mu and sigma now are really constrained to be quite equal and to live on this diagonal as long as we are concerned with Hordensky, so basically the whole class of scalar tensor theories. And so there is a consistency condition between mu and sigma, and this can help us in making some progress and also, I mean, optimizing our reconstruction of this function and guiding also our measurement of them with Euclid. And I must say, then I come to my conclusions, I must say that some of this narrowing and pushing mu and sigma to live on this diagonal, at least at earlier times, then maybe opening up a bit at the late times, comes from this complementary information from gravitational waves, and there will be more coming, and also eventually informations from using them as standard sirens, so information on the equation of state. But we already were doing some cleaning up of this possible space for mu and sigma to live just by using information that we have already from solar system, local test of gravity, but also just from theoretical principles, from requiring our theories to really be meaningful from a physical point of view, to do not develop instabilities, and one of the most common instabilities are ghosts. So from preventing ghosts to being out there, we can already exclude quite some regions. So, okay, so I think to conclude, this dark universe that we have in front of us, oh, and it is really dark, so I was trying to have an elephant here. It's the big elephant in the room, but it is also a dark one. And we are addressing it. We see it. We are addressing it. And I think synergy, again, is really what will be key. We have many wonderful measurements out there. Euclid will really allow us to make a big jump in terms of figure of merit, in terms of accuracy with which we can constrain this function describing the dark universe and how it affects large-scale structure. But also we will have many other measurements. And it's a complicated beast. So it's important to look at it from many angles and combine the information, because what we can conclude from one measurement can be very different from what another measurement can conclude. And I'll stop here. Thank you.
Thank you, Alessandra. Time for a couple of questions. So actually, I have one, which is your mu and sigma functions are focused on the linear regime of large-scale structure growth, right?
Yes.
So how much more information is there if you could push it to the
there is quite some information there. I think some of the forecast that I was showing done with Euclid specifications, they did try to include also some nonlinear. I'm not sure if the plot, I think the plot I showed was the conservative one, cutting out all the nonlinear. So of course, there's a lot that we want to dig out from the nonlinear. It's just hard to do it in a model-independent way. But we are getting there with emulators. So, yes.
All the way to the back. Try it.
So, Alessandra, your description of looking for modified gravity is a very statistical approach.
Yeah, true.
But what about a more detective-like approach, where you say, I'm going to try to understand what a modified gravity theory is going to do physically, and I'm going to look and identify certain objects that are affected most.
Yeah.
Two examples, the amount of halos, for example, and in the end galaxies, and the other one is the effect in the lowest density regions, the voids.
The voids. Yeah, so I really focus on, you're right. There are such things. There are also some trigger quantities that we can build. And the growth index that was mentioned before is one of those. So we have gone through that exercise, and we have learned what happens and what are some things that change when we modify gravity. And so we can definitely think about some specific measurements or combination of observables that would really trigger sort of whether it is lambda CDM or not. What I was trying to, the fact that I focus on this sort of statistical approach is because there is a lot of effort on measuring such things as mu and sigma, but I think it is really important that we stay away from parametrizations of them, such as of the type of W0 and WA. So the work, why we are trying to do this statistical approach is because we are really pushing for a non-parametric reconstruction of these functions. So Euclid will measure somehow this mu and sigma, but we rather don't want Euclid to tell us mu0 and mu-a. We want it to reconstruct it through binning. So that's why I focus on all this. But yes, I agree, there's a completely, I didn't talk at all about other more specific ways of measuring it, but there are, yeah.